Hello, pre-calc honors. Welcome to Flip This Classroom with Dr. Platko. Today we are on 5.5a. We're going to explore double angle and power reducing identities. So I want to tell you briefly about some of the main ideas before we actually write down the identities. Today, what we will be exploring is the sign of 2u. Something like this, the sign of 2u. Now, what we're looking at is this is a double angle. So if u is our angle, we're doubling it. That's essentially what it is. So the sine of 2u could be the sine of 60 if you're thinking of it as the sine of 2 times 30 degrees. Okay, so that's what we're doing. We're thinking of how could we double an angle and figure out what it would be. Another way that I want you to think about the sine of 2u is that it can be written as another way of doubling in math is by addition. It can be the sine of u plus u. And that can be a really helpful tool when you're doing proofs. So if you think about this, you've already learned this identity. This would be what we consider a sum or a difference. Okay, so they're directly related. A double angle can be related to a sum or a difference. We're also going to be talking about squares. So really, what else can we do to replace sine squared u? We can replace it with a variety of things. I'm going to show you those later. And then lastly, half angles. So let's say we wanted to know the sine of 15 degrees.
Elizabeth McElroy, please come to the office. Elizabeth McElroy to the office.
The sine of 15 degrees is found by taking half of 30. And so we're going to have to think about that. There's a formula or a rule.
Chandra Beetleson, please call the office. Chandra Beetleson.
For taking half of an angle, the sine of u divided by 2. You guys didn't really need to write too much of this stuff up here because we're going to talk about it a lot later. So what I need you to do right now is I need you to go back to your identity sheet. Back to here. Identity outline part 2. So we've already listed the sum and differences. We're now going to list the double angle identities. So the sine of 2u, that can be replaced at any time in any equation or expression with this, 2 times the sine of u times the cosine of u. The cosine of 2u actually has 3 different useful identities. And so you're going to have to choose carefully, depending on what you're doing, which one seems to be the best option. It could be cosine squared u minus sine squared u. You could replace cosine of 2u with 2 cosine squared u minus 1. Or you could replace it with 1 minus 2 sine squared u. Now, I hope you're sitting there thinking to yourself, why would we have these 3 different options? Well, these are all just Pythagorean relationships. So they're all equivalent to the cosine of 2u. One of our jobs later is to prove why sine of 2u is equal to this. So you could do any of the proofs for these based upon all the identities that you've learned before this section. The tangent of 2u, double angle is what we call this for tangent, is 2 times the tangent of u divided by 1 minus tangent squared u. While we're here, I also want to fill in the power reducing identities. I have to switch sheets, but you just need to look down. Power reducing is literally reducing the power of a function. So if we are given sine squared u, now you guys know that that has a Pythagorean relationship. We could replace it with sine squared equals 1 minus cosine squared. However, it could also be replaced with 1 minus the cosine of 2u divided by 2. And the reason why this is beneficial is because the exponent in this expression is the first power. And in calculus, it's a lot easier to work with first power or exponents that are 1 often, more often than it is to work with things that are squared or to the fourth power. So we can replace sine squared, power reduce the power so that the exponent up here is only 1. We can do this with cosine squared and tangent squared. And these are identities that you might prove in your homework, or we might do in class together. Cosine squared, again, could be replaced with 1 minus sine squared. However, we'd still have an exponent of 2. If we had 1 minus sine squared here, the Pythagorean identity, we still have this exponent of 2. So we're not going to use that. We're going to power reduce, and it would be 1 plus the cosine of 2u divided by 2. Lastly, the tangent squared. We all know that we could replace that with Pythagorean identity, but what we want to do is we want to power reduce. So it's 1 minus the cosine of 2u divided by 1 plus the cosine of 2u. All right, you will want to keep this sheet handy while you're working. So maybe when you come to class, I'm going to make a note to myself right now. When you come to class, I might hand these out to you. So I'm writing it on a piece of paper right now. Get trig people an identity sheet because you guys don't want to flip back and forth through your notes. So I'm going to hand you one. Okay, so we are going back to 5.5a. You've got the main ideas. Double angle, power reducing, and half angle is 5.5b. So we'll worry about that later. Example 1. Given the cosine of theta is 5 over 13, and it's our angle is between 3 pi over 2 and 2 pi. That means it's in a certain quadrant. Hopefully you are writing down which quadrant this is. In between 3 pi over 2 and 2 pi is quadrant 4. Find the sine of 2 theta, the cosecant of 2 theta, the tangent of 2 theta, and the cotangent of 2 theta. Notice that I did not give you identities for cosecant and cotangent. The first thing that I would do on this problem, and I hope you're thinking of it as well, is make a bow tie angle. So in the fourth quadrant, if we were drawing a bow tie, the side of the bow tie would look like this, but we only care about the fourth quadrant. So I actually don't need this part. That means that this is theta. It's always, the reference angle is always with respect to the x-axis. And cosine is adjacent over hypotenuse. So adjacent to theta is positive 5. It's also our x value. And the hypotenuse is 13. So we need to go ahead and figure out what our y value is. We're going to do the Pythagorean theorem. A squared plus b squared equals c squared. We know what c is. It's 13. I'm going to let a be 5. So I'm finding b. So 25 plus b squared equals 169. Subtract 25 from both sides, you get 144. B is equal to plus or minus the square root of 144, which is plus or minus 12. So you need to make an educated decision here. Is it positive or negative? It's negative because it's directional. It goes down. Okay, so it's asking me to find the sine of 2 theta. Luckily, you have an identity sheet. The sine of 2 theta equals 2 times the sine of theta, then times the cosine of theta. So substitute. You know what the sine of theta is, believe it or not. The sine of theta, this is what I'm looking for. I'm going to go off to the side. The sine of theta is opposite over hypotenuse with regards to your angle. So negative 12 over 13. So I'm going to put that in here, negative 12 over 13. The cosine of theta was given to you. You don't have to do anything. It's adjacent over hypotenuse, 5 over 13. So when we simplify, we're multiplying fractions. We have 2 times negative 12, which is negative 144. Sorry. 2 times negative 12 is negative 24, times 5 is negative 120, over 13 times 13, which is 169. And this is the answer that we're looking for. That is the sine of 2 theta. Double the angle. Okay, now the cosecant of 2 theta is really easy to find. It's 1 over the sine of 2 theta. That's how those identities work. So 1 divided by negative 120 over 169 is equal to, I'm going to use proper notation here, is equal to 1 times 169 divided by negative 120. So your final answer is 169 over negative 120, and it's simply the reciprocal of sine. This is the cosecant of 2 theta, the reciprocal of sine. Okay, let's try tangent. The tangent of 2 theta, you look at your identity sheet. Here's how you figure it out, identity sheet. 2 times the tangent of theta, which you guys are very capable of finding the tangent of theta, divided by 1 minus tangent squared theta. And I always double check. I've got to make sure I'm looking at the right identity. Okay, here we go. 2, the tangent of theta, I need to do some side work. Tangent of our angle up here, here's theta, is opposite over adjacent. So opposite is negative 12, adjacent is 5. So 2 times negative 12 divided by 5 divided by 1 minus, there's that tangent squared theta again. You have to understand this notation. This is tangent of theta squared. Order of operations is crucial here. 2 times negative 12 fifths is really 2 over 1. Multiplying straight across, you get negative 24 divided by 5. I'm going to divide that by, order of operations, we have to do this exponent first. 1 minus, I need to square this. That would be 144 divided by 25. Again, I am not going to simplify this expression or change to multiplying by the denominator or by the reciprocal until the denominator is simple. So if I look at this, this is what jumps out at me right here. And I need to combine these two things. So right now I have negative 24 over 5 divided by, this is really 1 over 1. So I need to multiply it by 25 on the top and 25 on the bottom. So 25 minus 144 over the common denominator, 25. I'm going to save myself some paper. Negative 24 divided by 5, bigger bar, 25 minus 144 is negative 119 divided by 25. Now that I have a fraction over a fraction simplified, I can multiply by the reciprocal. Let's talk about a couple things. You learned this a long time ago. Since this is multiplication here, you can divide this by 5 and you can divide this by 5. So negative 24 times 5, I think we talked about that earlier, is negative 120 over negative 119, which is actually positive 120 over 119. What were we solving for? Do you remember? It's the tangent of 2 theta. So, pretty simply, the cotangent of 2 theta is the reciprocal of that, 119 over 120. Next problem. Solve an equation that involves a double angle. If possible, find the exact value of the angle in the interval 0 to 2 pi. It's an exact value means no decimal. So that means, is it possible to use the unit circle that you understand? Okay, so no decimal, you're looking to use the unit circle, if possible. If you can't, then you can't. Now, it would help if I gave you an equation. So, 2 times the cosine of x plus sine of 2x equals 0. We're supposed to solve an equation. My question to you would be, is this quadratic? And you would say, no, there are no quadratic terms here. What should jump out at you is this right here. You should look at this equation and think and say, that's a double angle. That's what I need to start with. And know that you have an identity for it. And that identity should make your life easier. So copy down 2 times the cosine of x. It's not harming anyone. Plus, sine of 2x only has one option. The only thing that sine of 2x can equal is 2 times the sine of x times the cosine of x. Make sure you write everything down equals 0 every single time. Now, what we have is we have two different variables. We have cosines and we have sines, and we have a cosine in each term. So I hope you're thinking factor and you're thinking factor GCF. What can be taken out of both of those terms? You guessed it, 2 times the cosine of x. You need to hold this place with a 1, and then you need to hold this place with a sine. And you can always double check. 2 times cosine times 1 is 2 cosine. 2 times cosine times sine is 2 times cosine times sine. Okay, the multiplication property of 0 states that this has to be 0 in this equation, or this has to equal 0. To isolate our trig function, we would divide both sides by 2. So the cosine of x equals 0. That is something that you know on the unit circle. And we have to find the answers in between 0 and 2 pi. We're not using inverses. So where are our x values 0? On the unit circle, our x values are 0 at pi over 2 and 3 pi over 2. There are two solutions to this problem. Next one, subtract 1 from both sides. Showing all your work, sine of x equals -1. Where is it that our y values on the unit circle are -1? Y value is -1 down here at 3 pi over 2. So that's just, it's the same answer. You don't need to write it twice. These are your only answers. What this means is that you could put this back into the original equation. If you put this in your calculator, pi over 2, and put a pi over 2 right here, you'd get out 0. Go ahead and try it. Hit pause. Go ahead and try it. And moving on to power reducing. I've been told by the people above me that are teaching calculus that we just want to be able to use a power reducing identity. The book is not really set up to utilize them. The book is used to prove them, but I just want you to rewrite this expression. Okay, you have sine to the fourth. When you're in calc, you don't want to have a fourth degree expression. You'd rather have something squared. So I need you guys to look at this and recognize that this is really sine squared x squared. They're the same thing. If you square something, or if something's squared and you take it to the second power, 2 times 2 is 4. Now remember, our notation is weird. Okay, so in trig, this is an identity, and it can be replaced with our power reducing identity. So look at your yellow sheet. Power reducing identities, what do we replace sine squared x with? We replace sine squared x with 1 minus the cosine of 2x all divided by 2 squared. Now, what would we do with that? If we were in calculus, we would need to simplify it. So that means we take 1 minus the cosine of 2x divided by 2, and we multiply it by itself. And what's going to happen is this answer is not going to feel simplified to you, but it's a good tool for you guys to have as you move on. First, 1 times 1 is 1. Outside is a negative cosine of 2x. Inside, 1 times negative cosine of 2x. And last, a negative cosine of 2x and a negative cosine of 2x is a positive cosine squared of 2x. Careful when you write that. All divided by 2 times 2 is 4. So let's write this in standard form. Cosine squared of 2x. You have a -1 and a -1 here, so you have -2 cosine of 2x plus 1 all divided by 4. And what you have now is, believe it or not, it's a simpler expression because you have something that is quadratic. So instead of being to the 4th power, you have the 2nd power. Okay, before we end our video tonight, the hints and tricks on this page. Couple of different things. Let's say you were given 16 sine of x cosine of x. Well, we haven't talked about a 16 in a long time. But what should jump out at you in this problem is this. Sine of x cosine of x. You should get to a point where you can recognize that that looks like double angle. Double angle for sine, this looks very similar to what this is. So you're wondering if you can replace this with something else. So instead of having it be a 16 here, maybe we could actually get a 2 sitting right in front of it. Well, you all know that 8 times 2 is 16, sine of x times cosine of x. So instead of having this here, you can simplify this expression. This is 8, and then this is a double angle identity. So you guys need to recognize it forwards and backwards. Forwards is what I feel is sine of 2x equals this. Backwards is 2 sine of x cosine of x equals sine of 2x. Another hint that I showed you earlier today was when we had the sine of 2u, another double angle. Okay, I'm going to just make a little note over here that this was a double angle issue, and that this right here is also a double angle issue. It is really good to recognize that this is equivalent to the sine of u plus u. It's the same thing. Finally, let's say you were dealing with something like this, the cosine of 4x. You can see that in 2 different ways. It's all a game of how can you rewrite 4x. Well, you guys know that you could rewrite it as 2 times 2x. And in that case, it would be a double angle. This is 2, this is your u value. Or you could write it as a sum, which was our lesson from last class, from 5.4. So the cosine of 2x plus 2x. And it's just a matter of if you were doing a proof with the cosine of 4x, or maybe an application in calculus, would it be better to make a double angle, or would it be better to make sums? Last thing I have written on here is another double angle idea. Actually, I'm going to keep going with this. If this is double angle, again, here we are, double angle one more time, then how would you actually make a double angle out of this? Well, I need you to go to your double angle sheet, find cosine. And we could pick any of these. I'm actually going to pick the last one. So we know that on our yellow sheet we have cosine of 2u equals 1 minus 2 sine squared u. Well, in our case, what's our u value? Our u value is equal to 2x. So if we were rewriting ours, it would be the cosine of 2, this is 2x, equals 1 minus 2 times sine squared, and instead of having a u here, you'd have 2x. So I just want to give you guys some tools on how to actually apply these things. Okay? So I hope you have a good evening. This video was shorter than last time. I don't have any jokes or anything funny to tell you. So I do have a meeting to go to, and that's probably why I wasn't thinking about it. But I hope you are enjoying your day, and we will see each other soon. Have a good night.